Hi, my name is Jaekyum Kim, and I'm glad to introduce our paper on pure test time adversarial fine-tuning method for visual learning called Model-Agnostic Boundary-Adversarial Sampling for Test Time Generalization in Visual Learning. Our method is called MABAS. Let us first define the few-shot classification problem with some notations. At meta test time, which is only our interest, there are I few-shot tasks, each of which consists of support and query sets. K-way M-shot classification task means the task is comprised of K distinct classes and the support set contains M samples from each class. A classifier C trained with the meta-training dataset outputs a class prediction for a given sample, and the meta-test performance can be defined as the equation below. Visual learning method learned to classify query samples given only a few support samples with the meta-training dataset, and then transfer the trained embedding function f(phi) to the meta-test phase. However, in the meta-test phase, sample embeddings are not aligned well, and the classification boundaries obtained with labeled sample embeddings often fail to separate novel sample embeddings. This happens mainly due to the domain gap between the meta-training and meta-test datasets. To solve the issue, we proposed MABAS, which fine-tunes the embedding function solely in test time. It updates the embedding function with samples generated adversarially to the classification boundaries. Since MABAS is independent from the meta-training data, it works freely from the training test domain gaps. While MABAS is a model-agnostic method, it also doesn't require extra training steps or parameters, which makes it easily applicable to existing visual learning method. I'll explain how MABAS works. We start with a model-agnostic formulation that the base visual learning method predicts a novel samples class using score function h, which takes as input query embeddings. We define the classification margin as the score difference for the sample between two classes. For each labeled sample and each of the sample's possible attack target classes, MABAS creates an adversarial sample in the embedding space. The adversarial samples are created by moving support sample embeddings toward the classification boundaries. It then updates the embedding function f(phi) in the direction that increases the smallest classification margins of all the adversarial samples. Alpha xy, the average margin for xy, is an anchor that provides an upper limit for the adversarial sample's margins. We can integrate and express those objectives as the loss function shown here. And the final form of our fine-tuning loss function is shown here, where the regularization term is added for stabilization of the embedding space update. And we iterate the embedding function parameter update process. As a result, the embedding space becomes denser around the labeled samples, which makes the classifier robust to novel samples. I am going to provide examples of how MABAS is applied to existing visual learning methods. This base method is named MABAS. MABAS solves the multi-class SVM problem for support samples with a differentiable SVM solver, and it uses the SVM solution, which is the classification weights, to classify query samples. Its score function h is defined as the inner product between the weight for input class k and the sample embedding z. Plugging the definition of the score function h defined by Model-Agnostic into our earlier definitions, one can easily obtain the formulas for the generation of the adversarial sample and the adversarial loss function as shown here. Note that even for differentiable-based learners like this, the derivation of the adversarial gradient is done with the fixed classification weights. As a second example, we applied MABAS to the base method named fewshot without forgetting. It learns the embedding function as well as its attention-based classification weight generator in the meta training phase. Unlike the first base method, its score function is nonlinear as the cosine similarity is used. Using the definition of the score function, we can derive the equations for adversarial samples and the loss function as follows. Again, as we can see, the adversarial gradient is derived with the fixed classification weights despite they are differentiable with respect to z. Another example of application of MABAS is one to the standard transfer learning, which is a well-known approach to fewshot learning. Given the support samples, it computes the classification weights via the gradient descent. This base method has a characteristic that the classifier is not differentiable, differently from the earlier base methods. Since this method's score function has the same form as Model-Agnostic, the formulas for adversarial samples and the loss function are in the same form as well. We applied MABAS to the three representative fewshot learning method with diverse characteristics, which are Model-Agnostic, FSWF, and STL. And we performed experiments on MinImageNet, CIFAR-FS, and FC100 fewshot classification tasks. We showed that MABAS improves the test accuracies by large margins. It's 2.8 percentage point on average and 8.3 percentage point at most. Our method also achieved the state-of-the-art performance on 4 of the 6 fewshot learning tasks with fair backbone architectures. This is the evolution of average classification margin for support, adversarial, and query samples with FSWF on the 5-way fewshot meta test tasks. The plots show that the embedding space changes as the fine-tuning progresses, and it results in the increase of classification confidence. This is the TSNE visualization of the embedding space change brought by MABAS. Before applying our method, the embeddings from different classes are distributed in a mixed way with no clear class separation. As our method's fine-tuning proceeds, not only the support embeddings but also most core embeddings are condensed, and samples from distinct classes become distant. If you are interested in the full details, please check out our paper and the project website. Thank you for listening to our presentation.